Welcome to another Advanced Higher Chemistry video. This one is going to be on molecular orbitals and how molecular orbitals result in organic compounds either being coloured or not coloured. So two phrases that we use in relation to organic compounds that have molecular orbitals are HOMO and LUMO. Now, when molecules form, we have molecular orbitals. And as we know, the bonding orbitals are lower energy than the anti-bonding orbitals. And electrons will fill the lower energy orbitals, often the bonding orbitals, before they start filling the higher energy orbitals. That's just an extension of the Aufbau principle. Now, what this usually does is it leaves some anti-bonding orbitals unoccupied within the molecule. If you give a molecule enough energy, you can make the electrons excited from the occupied molecular orbitals to the unoccupied molecular orbitals. And a compound will absorb energy, causing that promotion or that excitation of the electrons. Now, the smallest energy gap between molecular orbitals within a molecule is between the highest occupied molecular orbital, what we call the HOMO. That's where the electrons are starting. They are in the highest occupied molecular orbital. And with enough energy, they can be promoted, excited to the lowest unoccupied molecular orbital, the LUMO. So you need to know HOMO and LUMO. Often it is enough to just say that there's an excitation from the HOMO to the LUMO, but I think and I would recommend that you learn what HOMO and LUMO mean: highest occupied molecular orbital and lowest unoccupied molecular orbital. So in a molecule like hydrogen, we would have the electrons in that bonding orbital in the middle, and with enough energy, one electron could move from the bonding orbital to the anti-bonding orbital. With enough energy, if you were to promote both electrons to the anti-bonding orbital, you would break the bond. And if you were using light energy to do that, that would be like the start of your free radical formation. You would break the bond entirely using light. So the HOMO, LUMO, and we would have electrons moving between them. Now, the size of the energy difference between the HOMO and the LUMO is what determines how much energy will be associated. So the bigger the energy difference, the more energy will be needed to excite or promote the electrons. So the size of the HOMO-LUMO gap determines the energy gap, which will then determine how much energy the light source or the radiation source must have in order to do that promotion or excitation. So on the left-hand side, we have a very large HOMO-LUMO gap, and on the right-hand side, we have a much smaller HOMO-LUMO gap. To do that, we have a big lightning bolt showing a big amount of energy on the left-hand side, and on the right-hand side, a smaller amount of energy. The bigger the energy gap, it means a higher frequency of electromagnetic radiation is required, which would then mean a lower wavelength. And you could be used to calculate that using what you already know, your E equals HV, or if it's per mole, E equals LHV. Now, colourless compounds versus coloured compounds. So the majority of organic compounds are actually white. That's why most medicines are white powders. This is due to them possessing a really large HOMO-LUMO gap, which means you would need a really high frequency electromagnetic radiation source in order to promote. And this high energy would require ultraviolet light. Now, because ultraviolet light doesn't have any colour, if a compound absorbs ultraviolet light and it's absorbing ultraviolet, it means everything in the coloured spectrum is going into your eye, and all the colours together is interpreted as white. So we would see the compound as white. No coloured light is being absorbed, so the compound will not appear coloured to us. And UV light is when there is a large HOMO-LUMO gap. Now in coloured compounds, if a compound is coloured, it means that there has been a lower HOMO-LUMO gap, and we will get on to how do we lower the HOMO-LUMO gap in the next slide. But if you've got a smaller or a lower HOMO-LUMO gap, some visible light, coloured visible light, will be absorbed, and the compound colour will be complementary to the colour absorbed by the compound, very similar to how the colours of transition metal complexes arise. So when you're asked about colours of organic compounds, you're going to be using the colour wheel in your data booklet, and you'll always be looking for complementary colours. And you could be told the wavelength that's absorbed or the colour that's absorbed, and be asked to say what colour the compound will appear. Or you could be told, oh, the compound appears this colour, so give a wavelength or a colour that it is absorbing. And remember, complementary means opposite. So for example, if a compound is absorbing red light, it will appear blue-green. If a compound is absorbing yellow light, it will appear blue. You're looking at opposites on the coloured wheel for complementary colours. You've got to keep that in mind. Now, how do we lower the HOMO-LUMO gap? Well, in the previous video, we looked at conjugated systems, and it's conjugation that results in a lowering of the HOMO-LUMO gap. Molecules with alternating single and double bonds create loads of unhybridized p orbitals. And where you've got unhybridized p orbitals, they can form overlapping pi bonds. And this constant system of a pi bond, then a sigma bond, then a pi bond, then a sigma bond, then a pi bond is called a conjugated system. And in a conjugated system, the electrons are delocalized. So we saw this in benzene, for example. Even though it's only got 3 double bonds, 3 pi bonds, the electrons are delocalized because essentially the positions of those double bonds is constantly shifting. And this is true for all conjugated systems. So conjugation, alternating single double bonds, lowers the HOMO-LUMO gap, and therefore will allow a compound to have a lower energy requirement, and it may cause it to be coloured. So conjugation lowers the HOMO-LUMO gap. Conjugation is alternating single double bonds over and over again. And they're more likely to be coloured, but they're not necessarily going to be coloured. So if you see a compound like that, you can talk about its likelihood of having colour, or if you're told that a compound is coloured, you could explain it in terms of conjugation, but don't assume that because there are some conjugated bonds that it's going to be colourless or coloured. So here we have an example. So in terms of energy, this is the HOMO-LUMO gap. Benzene and those aromatic compounds where they're in a ring, those always have very low HOMO-LUMO gaps. Then as we go to, instead of being a ring with this alternating single double bond, we go to a chain with alternating single double bonds. We're slightly higher in energy, but it's still conjugated, and there's still a possibility of the compound appearing coloured. And then at the top is where we've got an isolated double bond, where the electrons are not delocalized in any way, it's not conjugated, and it's very likely to appear white because it will be absorbing UV light. So here's an example of a highly conjugated system. If we're looking through it, it doesn't matter if the double bond is between 2 carbon atoms or between a carbon and an oxygen. You're just looking for an alternating pattern of single and double bonds. So in this molecule, the conjugated part is that entire region. So this molecule is very likely to be coloured. In this compound, if we're looking for conjugation, remember it has to be alternating single and double bonds. So this molecule actually has 2 regions that are conjugated. We've got 3 conjugated bonds here, and we've got 2 conjugated bonds here. This carbon here that doesn't have a double bond as part of it is an sp3. It would have 2 hydrogens coming off of it. That sp3 carbon always interrupts the conjugation. And so we've got these 2 individual conjugations, which actually lowers the likelihood of it being coloured because each one is going to be independent. Now here are two famous conjugated molecules. They're both based on conjugated rings called porphyrins. Now depending on what you put in the middle, because these are both ligands, you put a metal in the middle. Depending on what metal goes in the middle, you end up with a very different colour. So if we put iron in the middle of that porphyrin ring, that is a biological molecule called hemoglobin, and that is responsible for binding oxygen in your blood and giving your blood its red colour. If we put a magnesium inside the porphyrin ring instead, this is a really important molecule in plants. It's the molecule that makes them green. It's chlorophyll, and without chlorophyll, plants wouldn't be able to absorb light energy. And part of the light energy it's absorbing is due to the fact that it's conjugated, so it's absorbing coloured light. Now, indicators rely on conjugation as well. A good example is phenolphthalein. The reason I'm showing this example in the video is because phenolphthalein has frequently been asked about in past papers. So phenolphthalein in alkali is bright pink. So if it's bright pink, that means it is absorbing some coloured light. And that is because it is fully conjugated. Even though we have got what appears to be a carbon that's got 4 different groups around it, these benzene shaped or type rings are conjugated with one another. It's a bit more complicated as to why, but they are conjugated and it's bright pink. Now, as you do a titration and you add hydrogen ions to it, what happens is that indicator breaks apart, and when it's broken up, you destroy the conjugation and that indicator becomes colourless. And this is how a lot of indicators work. Adding a hydrogen on interrupts the conjugation in some way, which then changes the amount of visible light, or the wavelength, sorry, of visible light, changing the colour. So an understanding that conjugation is involved in indicators is a good thing to know. The final thing we need to do, or just need to be aware of when it comes to coloured compounds, is the word chromophore. So chromophore, particularly in older past papers, is a word that will be used, and it still can be used in modern advanced higher chemistry papers. And it just means the region of an organic molecule that results in visible light being absorbed. And you know, if it's got this highly conjugated system, we would call that highly conjugated system a chromophore. It's got a low HOMO-LUMO gap, therefore can absorb visible light. And any molecule that has a colour contains a chromophore. So this word is just something to be aware of. If, however, you're asked, why is this compound coloured, you cannot answer with, it contains a chromophore. You need to be able to explain what is meant by a chromophore, and in terms of a chromophore, what we're meaning is a conjugated system, that alternating single double bond repeating, that results in a lower HOMO-LUMO gap, and therefore visible light being absorbed. But the word chromophore is one you need to be aware of, but I would never include the word chromophore as an answer to a question. Always go into more detail about what is conjugation and what effect conjugation has in terms of lowering the HOMO-LUMO gap. So that has been our video on organic compounds, conjugated systems, and why the colours of organic compounds can change.